Hi, let's take a look at an example of an isolated system where we have to consider friction. So, say we have a 40 kilogram mass sliding down a 15-degree ramp a distance of 1.5 meters from rest. And there's a coefficient of kinetic friction between our object and the ramp of 0.23. Now, at first, this doesn't necessarily seem isolated because that object is touching a ramp, but when we look at the forces, gravity's involved, and gravity's a conservative force, so that's going to show up as potential energy. We have kinetic friction, which is really, we said, a change in internal energy, so friction is separate from the other forces, and the only other force we'd have to deal with is the normal force. And as long as the object is sliding along the ramp, that normal force is going to do no work. So we could treat this like an isolated system and say that our change in potential energy plus our change in kinetic energy plus our change in internal energy has to equal 0. So for potential energy, we can choose the lowest point, the bottom of our ramp, and call that 0 potential energy. That would be our final potential energy. Our initial potential energy is based on gravity, and it's just going to be equal to our mass times the strength of gravity times the starting height of this object, y. And that starting height would just be the length of the ramp times the sine of the angle of the ramp. So our change in potential energy would be minus, because we end at 0, start at m times g times y. So our change in potential energy is minus the mass times the strength of gravity times the length of the ramp times the sine of the angle of the ramp. Now, for kinetic energy, if it starts at rest, our initial kinetic energy is 0. Our final kinetic energy is 1/2 mv squared. So our change in kinetic energy is just 1/2 times our mass times our final speed squared. And for our change in internal energy, the change in internal energy is the force of kinetic friction times the distance that the object slides. And when friction is there and present, friction is increasing the amount of internal energy that we have. So, we need to calculate our force of kinetic friction. Well, the force of kinetic friction is the coefficient of kinetic friction times the size of the normal force. And to find the size of the normal force, well, the force of gravity is pulling this object essentially down the ramp and into the ramp perpendicularly. Well, this perpendicular component of the weight is just the weight times the cosine of that angle theta. So that means our force of kinetic friction is going to be our coefficient, mu sub k, times the mass times gravity times the cosine of the angle of the ramp. So to get our change in internal energy, we take our force of kinetic friction and multiply by the distance, which is just the length of our ramp. So this term and that term all added together should equal 0. Well, that means that my final kinetic energy is going to equal the mass times gravity times the length times the sine of theta minus the coefficient of kinetic friction times mass times gravity times length times the cosine of theta. And we could do a little bit of cleaning up here when we solve. First off, mass cancels out everywhere. So this would be true for any massed object. Now, there's, when I multiply by 2, going to be a 2 in each term, a strength of gravity each term, and the length in each term. So I could bring out a 2 times the strength of gravity times the length, and that would leave the sine of my angle minus the coefficient of kinetic friction times the cosine of my angle. But I could go even one step further, and I could pull out a factor of the cosine of the angle. And I'd have 2 times gravity times the length times the cosine of my angle, all multiplied by the tangent of the angle minus the coefficient of kinetic friction. Now, back when we talked about ramps for the first time and friction for the first time, we said we could calculate the coefficient of static friction as the tangent of the maximum angle where an object will remain at rest. So in order for this to work, we would have to have an angle great enough so that our coefficient of kinetic friction is smaller than the tangent of that angle. Otherwise, the object's going to sit there at rest. And that would be sort of shown by saying we'd either have 0 in here, or in the worst case, a negative number under a square root, which we can't do with real numbers. Well, if we take the tangent of 0.15, or not 0.15, the tangent of 15 degrees, the tangent of 15 degrees is about 0.26, which is greater than 0.23, so we do get a real solution, and when we multiply everything and take the square root, we get a speed at the bottom of the ramp of 1.04 meters per second. Thanks for watching.